Alright, so we're going to look at hyperbolic functions, and what you're going to focus on in this tutorial is the definition of hyperbolic functions, as well as the comparison between hyperbolic functions and trigonometric functions. And of course, we're also going to touch a bit on the identities, as well as the derivatives of hyperbolic functions. Okay, so if you want to try to compare trig functions, okay, if you want to try to compare uh, trig functions as well as hyperbolic functions, I'll just say hyperbolic functions like that. So what you need to keep in mind is that for the trigonometric functions or the trig functions, these are related to the unit circle. Okay, so whenever you are talking about trigonometric functions, all you are talking about, you are just relating everything to the unit circle. Even the identities, you find that in one way or the other, they all just come from the unit circle. All right. Then for hyperbolic functions, or maybe we have said this one related to uh, related to the unit circle. Uh, okay, so we relate trig functions to the unit circle. Then for hyperbolic functions, we relate this to the what? I'll just say relate to uh, hyperbola. Hyperbola. All right. So what do I really mean by saying we relate trig functions to the unit circle and the hyperbolic functions to the hyperbola? So what this means is this: if we, let's say we have our unit circle, um, we have a unit circle like this. Okay, all right. So let's say we have our unit circle like that. Okay, something of that kind. Not really perfect, but at least it gives us a picture of what we are talking about. So let's say we have a point here. Okay, we have a point there, and we know that the unit circle has a radius of 1. So here at this point we have what? We have r, and we note that our r in this case is equals to what? Is equals to 1. Okay, so for the unit circle, or for the circle itself, the standard equation of the circle we did under analytic geometry, or we're talking about conic sections. We learned that x squared plus y squared is equals to 1. I don't have to put a squared over with the b squared there, because a is basically equals to b, and we understood that that's why the eccentricity is equals to 0, because the value of a and the value of b is simply the same. So if we say we have our r there, then we have our angle here theta, meaning at this point we are supposed to have r comma what? R comma theta, which is simply the same as what? X comma what? X comma y. And we understood this better when we are talking about polar equations or polar coordinates. Okay, so we want to relate what the value of x and y is at this point. Okay, and I believe you'll be able to understand where the identity cos squared um, cos squared of x plus uh, sine squared of x is equals to 1. We have been working with this identity for a long time now. We know it under trig identities, and we're going to understand here where it simply comes from. Okay, so in this case, our value of x, okay, how to find our value of x there? We are going to say is what? Is r cos what? R cos theta, meaning our y is going to be r sine what? R sine theta, and those are the coordinates for what? The coordinates at that point there. So when we get these values, or when you get that expression and replace it in what? In this equation here, what you're going to have is that you're going to have uh, r squared cos squared of theta plus r squared sine squared of theta is equals to 1, which is that one there. But this does not really resemble that one, simply because we still have r. But that's not really a problem, because we know, or we have understood, that our r for the unit circle is a 1. So 1 squared is still 1. So that's why we have our cos squared of theta plus sine squared of theta being equals to what? Being equals to 1. So that's why I was simply saying the trigonometric functions, they relate to the unit circle. For the hyperbolic functions, we relate them to the hyperbola. What does this mean as well? If we have that as our vertical axis and we have that as our horizontal axis, then we have a hyperbola of that kind which opens to the right. So we are going to have a point here, a point right here. We can put it anywhere, it doesn't really matter. And we know that the general equation for the hyperbola is x squared minus y squared is equals to 1. This is the general equation for what? The general equation for the hyperbola. But of course, we have a squared down here and b squared down there. But I don't really have to put it simply because sometimes the value of a and the value of b are also the same. But it's not always the case. Sometimes they are different. Sometimes they are the same. All right. So in this case here as well, instead of us now saying we are going to have a cos squared of theta, no, here what you're going to have is um, we're going to have something that is called cosh. Okay, sometimes you can just call it the hyperbolic cosine, of which you can write it as um, cos hyperbolic cosine squared of theta minus hyperbolic sine squared of theta is equals to what? Is equals to 1. And that's the that's the that's a relationship that we're talking about there, and this is simply one of the identities that we're going to be using over and over again as we talk about hyperbolic functions. So the key thing to remember is um, trigonometric functions relate to the unit circle. That's how you differentiate the two, because immediately if you just try to combine the two, you're going to miss the point, because even to some cases, as you differentiate, you're going to find that the result of the dy dx that you're going to get for the trig functions and for the hyperbolic function to some cases is going to be different. So we should just keep in mind to say, okay, these relate to the hyperbola and these relate to the unit circle. So we really need to get that basic understanding. And to focus on the hyperbolic functions now, if we are to talk about the definitions, we should also keep in mind to say hyperbolic functions, they are just a combination of exponential functions. Okay, they are just a combination of exponential functions, and the basic one that we use is simply the hyperbolic cosine and the hyperbolic sine, the cosh or the sinh. So the hyperbolic sine, which is this one, sometimes they call it a sinh, sometimes you can call it a hyperbolic sine. It's up to you, as long as you know how to write it. Okay, so the definition for the hyperbolic cosine or the cosh is I'll say hyperbolic cosine of x is equals to what? 1 over 2, okay, e to the x plus e to the minus x, like that. Then the hyperbolic sine, okay, the hyperbolic sine of h, no, not h, but x. Hyperbolic sine of x is equals to 1 over 2. Instead of having a plus, you're going to have e to the x minus e to the x, e minus e to the minus x there. Okay, those are the basic definitions for hyperbolic functions. So if someone asks you to define the hyperbolic cosine, just give them this expression here. For the hyperbolic sine, that's the expression there. Okay, so we'd also want to try to touch a bit on the derivatives of hyperbolic functions. But before we do that, I believe it's key that we note down the identities that we're going to be dealing with. We are going to use them a lot, more especially when we're talking about the inverse derivatives of hyperbolic functions. The first one is the one that we came up with earlier from the equation of the hyperbola, which was hyperbolic cosine squared plus hyperbolic sine squared. Of course, we have x here, and we have x there is equals to 1. Then the second one that we're also going to be using is the secant hyperbolic secant squared of x plus um, hyperbolic tangent squared of x is also equals to 1. Then we're also going to say hyperbolic cotangent squared of x minus hyperbolic uh, cosec, okay, cosec squared of x is also equals to 1. So we need to familiarize ourselves to like with these identities. Okay, we are going to use them a lot. So these are the common identities that we're going to be dealing with. Okay, so we're going to start with the basic one in terms of the derivatives. So we are going to start with the sign, of course. So if we say y is equals to uh, hyperbolic sine of x. I want to find what the gradient function is, or the dy dx as we commonly call it. Um, Here you're going to have your y prime, or the dy dx. You just say dy dx, or in this case, let me just write it as d um, d dx. Hmm. I think let me just use y prime. It's fine. Yeah, if I just say y prime will be equals to, so when you're differentiating sine, hyperbolic sine of x, you're going to get of course hyperbolic cosine of x. So this is your what, your dy dx. If you say your y is equals to hyperbolic cosine of h of x, what you're going to get as your y prime or your dy dx will be what, will be positive sine, hyperbolic sine of what? Hyperbolic sine of x. But wait here. When you're talking about trig functions, we said when y is equals to cos of x, meaning your y prime will be equals to minus sine of x. Why are we really saying that? Where is the negative going? Okay, so what happens here is if you look at the definitions, okay? If you look at the definitions here, then if I had said my y prime of hyperbolic cosine is equals to minus hyperbolic sine of x. um, Here's what we could have. If we say y prime is equals to minus, then hyperbolic sine of x is 1 over 2, open bracket, we have e to the x minus e to the minus x. So what you're going to have as the y prime will be equals to what? Will be equals to uh, e to the minus x um, over 2 minus e to the x over what? e to the x over e to the x over 2 there. Okay, which is not the case here. Okay, which is not the case here, because um, if this is what we have, then we pick this and differentiate it. Believe me, you are not going to get this. Okay, that's not what you're going to get, because if you say you want to differentiate, if you want to say you want to differentiate 1 over 2 of e to the x plus e to the minus x there. So what happens here is that you're going to have, if I write it as 1 over 2 e to the x plus 1 over 2 e to the minus x there. So when you're differentiating exponentials, differentiate the power there multiplied by the coefficient. Here, since it's 1, you're still going to get 1 over 2 e to the x. Then here, differentiate the power here, which is minus x, that will give us negative 1, multiplied by the coefficient, that will be minus 1 over 2 e to the minus x there. So this is the derivative that we get. And you look at this derivative here. This is simply what? This one here, the sign. So when you look at this one here, it's something very different there. So you can understand it better if you try to differentiate the definition there. Okay. So that basically means the derivative of the hyperbolic cosine of x is equals to hyperbolic sine of x. Okay, so what about if you have y is equals to hyperbolic tangent of x? Okay, hyperbolic tangent of x. So when it comes to these just we use the same ones for trig. Okay, here we know we are going to get for trig, we know we are going to get sec sec squared of x. So meaning we are going to get hyperbolic sec squared of x. So that will be hyperbolic sec squared of what? Sec squared of x, which is also equals to which I believe is also equals to 1 over minus 1 over hyperbolic cosine of h of x there. Okay, so what about when we have the cotangent, hyperbolic cotangent of x? Okay, still the same for, we're still going to use the same as for trig. We are going to get minus c uh, hyperbolic cos x squared of x, okay, which in turn is also equals to, if you look at the identities there, which is this part here, okay, which is that part there. Our cosec there is equals to 1 minus c hyperbolic cotangent of h of x, and again we can say this is also equals to uh, minus 1 over hyperbolic sine squared of what, of x. All right, what about what about the what about this, the when we have y is equals to sec, okay, hyperbolic sec of x. Okay, so this will simply give us something like minus hyperbolic tangent of x, then hyperbolic secant of h x there. Okay, so I guess the remaining one is now for what, for cosec. So if we say y is equals to the hyperbolic cosec of h is we are going to get we're still going to get something like minus uh, hyperbolic cotangent of h of x, then hyperbolic of cosec of what, cosec of x, and that's what we get right there. So it's very important that we keep these derivatives dear to ourselves as we look at the inverse hyperbolic functions, the derivatives of inverse hyperbolic functions. We are really going to use this, and more especially the identities there. So that's all in this video. Thank you very much for watching.